Alrighty. So the first thing that we're going to talk about today are guided beam springs. So the guided beam spring is the most commonly used type of spring structure found in surface micromachined MEMS devices. So I'm going to try to draw a picture here. So from a top-down view, we're going to be looking at something akin to this. I'm going to draw an H-like structure here. And I'm going to subdivide this structure into smaller constituent parts and talk about them here really quickly. So let me actually just make a note that this is a um, top-down view. An arrow pointing up this way so that we ensure that's what's going on. So I'm going to kind of cut off the end of these beams here. And I'm going to denote them with something really quickly. A moment. So these are where our anchor points are going to be. So this is where this suspension structure is mounted to the substrate in some way, shape, or form. And then I'm also going to cut off the other side of these beams to where this area in the middle is a plate that might serve as a proof mass or something like that in our system, okay? So we're going to assume that the anchor structure cannot bend, rotate, deflect, and all that kind of stuff, as well as the plate will not bend, rotate, or deflect. So the beams are actually just the part that's connecting the central plate to the anchor, okay? So these beams are going to be characterized by some particular length, L like so, as well as some particular width. And I'll define the height here in just a moment when we look at kind of a side view. And we're going to say that in this particular system, we are going to have some type of force directed down into the page that's going to cause this whole suspension system to move. Okay. So this is what our top-down view would look like, and then our side view would be something akin to this. Okay. So I've got my anchor structure here, and I'll put some more detail on that in a moment. Um, this is where my plate's going to be, and I'm going to try to connect this without it looking too crappy. And then kind of a similar thing on this side. And I'm going to put those little dash lines to demark the different pieces as well. So this is once again our plate. We had some force acting on it in this direction. These are our anchors affixing things to the substrate. And we're going to define our height direction here. So it's just the thickness of the beam that is undergoing deformation. Okay. So in this particular system, we have four springs connected between the plate and connected between the anchor points. So we have a system of four springs that are physically connected in parallel. Okay. The easiest way for us to approach analyzing a structure like this is to consider each one of these guided beam springs as two cantilever beams springs with a length of L over 2 that are connected in series. So because I'm talking about series and parallel springs and stuff like that, we need to make sure that we have some understanding of how to find equivalent spring constants for those particular configurations. So I want to talk as kind of a sub thing on this um, about Hooke's law for parallel and serial springs. Okay. So we've already talked about Hooke's law briefly in this class, and you guys had it in your physics classes and stuff like that. So this is what we've been using to determine the spring constant for our system, but in its most basic form, Hooke's law is simply F, our force, is equal to spring constant K times X, our spring displacement. Where I'm just going to annotate this really quickly. So this is force measured in newtons. K is spring constant measured in typically newtons per meter. And then lastly, we have displacement measured in, I'm going to say meters, but obviously on the micro scale, it's more likely to be micrometers, nanometers, that kind of thing. Okay. So whenever we have two springs connected in parallel, might look something like this. Okay, so I've got a plate here, plate here. I'm going to draw some spring right here, represented by some spring constant K1. Another spring right here, represented by some spring constant K2. And then we're trying to pull this system apart by applying forces in opposite directions like so. So let's call this, yeah. So our total force in the system will be given by the expression F total is equal to F1, so that's the force that's acting on spring 1, plus F2, the force that's acting on spring 2. Now, it should be fairly obvious, but each of these springs, because they are connected in parallel, are going to experience the same displacement, right? So one spring isn't going to be able to stretch any more than the other spring because of the way that these guys are physically configured. So I could substitute in here K1 times my displacement X plus K2 times my displacement X. And there's obviously a common factor of displacement here, so I can take that out, leaving me with K1 plus K2 times X, or some equivalent spring constant KEQ times X, where I think quite obviously KE2 is just the sum of K1 plus K2. Okay. So whenever we have springs connected in parallel, they're equivalent spring constant is just the algebraic sum of the spring constants of each individual spring. Okay. Whenever we have two springs are connected in series, it'll look something more akin to this, okay? So once again, I'm going to have my little plate thing. Here's my spring with a constant K1 connected in series to a second spring with a spring constant K2 like so. And once again, I'm just going to pull on this structure. Okay. And now we're going to see that instead of the displacement being a constant, the amount of force is going to be a constant, right? So we could say that our total displacement will be x total is equal to x1, the displacement experienced by spring 1, plus x2, the displacement experienced by spring 2. Putting those in terms of our common force, that's going to look like F over K1 plus F over K2. Pulling out that factor of F, we have 1 over K1 plus 1 over K2, or F divided by our equivalent spring constant, where in this case, KEQ is the sum of the reciprocals of our spring constants, and then we take the reciprocal of that sum. So for those of us like myself that are electrical engineering inclined, springs combine like capacitors. So springs in parallel combine like resistors in series, and springs in series combine like resistors in parallel. Okay. So using this information, where we're going to consider a guided beam spring to be two cantilever springs connected in series, where our length term is just divided in half, we can say that for a single guided beam spring, our spring constant KGB is going to be 2 over 3 EI divided by L over 2 quantity cubed. So just to make sure we all know where this is coming from, right? The spring constant of a single cantilever was given as 3 EI over L cubed. We're taking that length and cutting it in half because we're treating that guided beam like two springs connected in series. And this factor of 2 is coming from the fact that each of those halves are going to have the exact same spring constant. So I'm just adding 1 over K1 plus 1 over K1 gives me twice over K for the cantilever beam, okay? So now playing around with things really quickly here, just algebraically, right? So I'm going to have a factor of L cubed in the denominator of my denominator, so I can move that up to the numerator. So I'm going to have that 2 survives. Then I'm going to have the L cubed. And then because I have, and I know this is going to be annoying, a factor of 2 cubed in the denominator of the denominator of the denominator, that's going to look like a factor of 8 getting multiplied by that 3, giving me a 24 EI here. Oh, and I forgot the to the -1 thing here. My apologies. So I'm going to flip this guy over and get rid of that 24 over 2, leaving me with a spring constant of 12 EI over L cubed. Okay. where, just to reiterate here, that L is the total length of the guided beam spring. Okay. So actually, let me scroll back up here really quickly. So for this particular system, where we have 4 of those guys connected in parallel, we would actually wind up taking this single guided beam spring constant and then just multiplying that by a factor of 4 to figure out what the equivalent spring constant that our plate sees when we try to move it, right? Okay. So using Hooke's law, then we can see very easily that the displacement in this system is going to be our applied force times L cubed over 12 EI, where that's just X is equal to F over K. All right. So the last type of spring that we need to concern ourselves with are torsional springs. So torsional beams are used to create large angular displacements in a MEMS device, like we saw on the very first day of class with those TI digital micromirror arrays, okay? So essentially, we're going to have a beam that's anchored somewhere, and then we're going to attempt to twist the free end of that beam. So I'm going to attempt to draw this, and again, this is relying on my shitty drawing skills, so I'll pre-apologize here. But we should have something like this. So I'm going to say that the left-hand side of this guy is where we have things that are anchored. And I'm attempting to draw that this guy is getting twisted in some way, shape, or form. And I'm going to define a few things here. So this dimension I'm going to call A. This dimension is going to be B. Then we have our length here. Okay. We're going to have some angle here, theta. Okay. So this is by how much it's been rotated out of, perpendicular to that axis like we had originally have it. And then we're going to have some torsional moment, MT, acting on this system that's causing the twisting. So in this case, the angular displacement observed at the end of the beam is given by the mathematical relationship theta will be equal to our torsional moment MT multiplied by our beam length L divided by J, the moment of inertia for the torsional bar, times G, the modulus of elasticity. Okay. So let me just annotate this thing really quickly here. So this MT is torsional moment measured in Newton times meters. Okay. The length is just L. Actually, I'll just write it down just for the hell of it so that we make sure everything's going on right. So length measured in meters J is once again the moment of inertia, which is going to be measured in meters to the fourth power. And lastly, we have our modulus of elasticity. I didn't write the units down for this, but this is the same modulus of elasticity with symbol G that we talked about in the last class meeting, and I think I talked about them there. Having to do with shearing strain. Okay. So in a MEMS device, we're going to be dealing with bars or beams having rectangular cross sections mainly. So that's what I'm going to deal with mostly. So for a beam with a rectangular cross section, and I'm going to put a caveat here. I'm going to say that A is greater than or equal to B. So B is going to be the smallest of the thickness dimensions of the beam. Okay. The moment of inertia J will be given by AB cubed times 1/3 minus 0.21 times the ratio of B over A multiplied by 1 minus B to the fourth power over 12 times A to the fourth power. Close that off. Okay. Andrew, you have a question?
Yeah, you might have said this earlier already. Did you say theta was in radians or degrees?
So theta should come out to be in radians. Yeah. Yes.
For the G, he says modulus of elasticity, but I thought it was the modulus of rigidity. Because it's a shearing.
So let me go back here. I might have misspoken. Shearing modulus of elasticity measured in newtons per meter squared. So let me just actually, since I have that out here, newtons per meter squared. So if we look at the dimensions of this just really quickly, right? So we have Newton meters times meter, so that's Newton times meter squared, divided by newtons per meter squared times meters to the fourth power, so that's also going to be newtons times meter squared. So we're going to wind up getting a dimensionless quantity, which is why I say that the angle is going to be in radians. Literally forgot I had the notes from the other day right there in front of me. All right, so if we apply Hooke's law for torsion, that's going to be our torsional moment MT is equal to our torsional spring constant, which I'm going to label as K theta times, and in this case, our displacement is going to be the angle that we've twisted this guy by. So rearranging that expression allows us to determine our angle well, that's literally, hold on, that's just me rewriting the same damn thing. Actually, let me go back just a moment here. So if I look at this expression for torsional moment, Hooke's law for torsion, and I look at this expression right here for our angle, we can kind of deduce what our spring constant is going to be from these two relationships, right? So what we'll find is that our spring constant K theta is going to be JG over our length. So substituting in a factor of G in the numerator and L in the denominator by the J that we have above, we wind up getting G times AB cubed over our length. 1/3 minus 0.21 B over A times 1 minus B to the fourth power over 12 A to the fourth power. And this particular spring constant is going to be measured in Newton times meters instead of Newton per meters, like the other spring constants where we just had elastic deformation, right? And I've just got another little note down here, so I'm just going to go ahead and write that. So for a torsional moment, MT, caused by a force F applied a distance L away from the anchor point, our angle of rotation is just FL over our spring constant. We make that look more like a theta. All right, so let me just recap things very briefly here. These are the 4 different types of springs that we are going to be dealing with. The overwhelming majority of the time, we're going to be dealing with guided beam springs for most of the things. We will work some examples dealing with cantilevers, specifically extension rods. The torsional ones are the ones that we're going to see the absolute least. So just as a heads up. So this is a review, or this concludes the review of the mechanics side of things. So now we need to start the review of the electrical side of things. So this is where all of the electrical students are going to be bored and all of the mechanical students are going to be like, oh, well, now he finally is talking about something he might know about. So, all right, so let's do a very brief review of electrical properties. So we're going to start with some very basic information about semiconductors. So there are multiple different types of semiconducting materials. We can either have single element semiconductors. So let me just put a note here. So single element semiconductors. So this would be things like carbon in the form of a carbon nanotube or graphene, because diamond is also made purely of carbon, but that is a really, really good electrical insulator. Silicon would be another single element semiconductor. Germanium, GE, is another example of a single element semiconductor. Or we can have compound semiconductors. So in our compound semiconductors, we might have things like silicon carbide, where we just have a compound semiconductor made of two materials that could have been acting as a semiconductor on their own. Or we could have things like gallium nitride or zinc selenide, or cadmium sulfide, something like that. Let me make sure that that looks like a thing. CDS. All of those are examples of compound semiconductors where it's made of multiple materials, or excuse me, multiple elements, and not elements that exhibit semiconducting properties on their own. Just for the hell of it, I'm going to pull up a periodic table real quick because I think this might help better explain this. I might be over explaining it and you guys already know what the hell I'm talking about, but just in case. Let's see. Get rid of that thing. Periodic table of elements. Let me get a good looking picture here. Okay. So all of the single element semiconductors are right along here. Okay. And it's just these guys in particular. Once we get to tin, lead, and the metals and stuff like that, it no longer starts behaving as a semiconductor because, as I just mentioned, they are metals, so they're highly electrically conductive. For our multi-element semiconductors, like I said, we can mix silicon and carbon together. We could potentially mix germanium and carbon or germanium and silicon as some sort of semiconductor alloy. Not sure whether or not that's actually done, but for our vast majority of our other compound semiconductors, we're usually going to take an element that's one column to the left of our elemental semiconductors and one column to the right of our elemental semiconductors and kind of add those guys together. We may also go two elements to the left and then two elements to the right. Essentially, we're always going to have some neutral thing, but it's around that one particular column, okay? There are some pretty complex ceramic semiconductor materials and stuff that we could get into as well, but we're not gonna talk about them too particularly much because they're not really used to make microstructures very often ever. So the kind of space that we're gonna live in is gonna be really between this column right here and this column over here, okay? And we're gonna be looking more towards the top of the periodic table versus these guys down at the bottom, okay? So the thing, sorry, that was too far. So the thing that makes a semiconductor material different from an insulating material or a conducting material is its energy band structure, okay? So other than, I hope, my undergrad EE students, how many of you guys are familiar with energy band structures? All right, let me open up the floor to including my EE students. How many of you guys are familiar with energy band diagrams? Okay, like literally two or three of you. Okay, more people are doing it. Great. All right. So I'm going to try to explain this as simply as I can. We're going to look at some basic energy band structures here really quickly. Okay. So on the leftmost side over here, I'm going to put an insulator. Okay. Okay. So the energy band structure for an insulator should look something akin to this. So this is the top where we're looking at electron energy measured in electron volts. And way down here is going to be 0. And so I'm going to have this region right here. Okay. And I'm going to label this particular energy level with EV. Okay. So this is the valence band energy. Okay. And so for an insulating material at T is equal to 0 degrees Kelvin, but usually for practically all temperatures, unless we get really, really hot, this guy is going to be completely full of electrons. Okay, so that's what I'm trying to represent by coloring that box in black there. Okay, and then up above this, we are going to have what's called the conduction band. Okay? So this label EC is where the conduction band begins, and then all occupiable energy states above this are all part of the conduction band. This is going to stop when we get to what's called EC plus chi, where chi is the electron affinity. And so if we are able to pull an electron above that particular energy level, we consider that we've removed that from the crystal structure itself, okay? So we've just completely stripped that electron out. So it's not free for conduction, it's no longer part of that structure, okay? So an insulator is typically characterized by its large energy band gap, E sub G. So that's just the difference between EC and EV. So I'm just going to put a note here that this is large. Large in this context would be 5 to 10 electron volts of potential difference there. Okay. To contrast that, here in the middle, I'm going to put a metal. Okay. So in a metal, we're going to have something more akin to this. And there are a couple of different energy band structures that are associated with metal, but they're all at least pretty close to this. Okay. So I'm starting again at the bottom and drawing my valence band. So here's EV. In many metals, the conduction band will actually start a little bit below where the valence band ends. So essentially, we have an overlapping band structure like this, which means by default, we have some electrons that are available for conduction. Okay? We don't have to do anything. They don't have to be thermally excited or excited by photons or anything like that. They're already just in the conduction band as well, which is why we typically consider metals to be really good conductors of electricity, okay? Because there are already electrons in a spot where they're free to move around and conduct electricity throughout a device. So the energy band structure for a semiconductor is going to look very similar to that of an insulator, except the band gap is going to be significantly smaller. Okay. So here's our filled valence band. I'm going to say that my conduction band starts down here so that my band gap was significantly smaller. Here's EG, and this is going to be 0.5 to 2 electron volts for a semiconducting material. Okay. Where this is EC plus chi, and that's electron energy. So for silicon, this band gap is 1.12 electron volts. For germanium, 0.66 electron volts. For gallium arsenide, 1.4 electron volts. Okay, so different semiconductors have different band gaps, meaning that they are going to have different electrical characteristics and all of that kind of good stuff. So most semiconductor materials, at least the ones that we're going to be dealing with to make microstructures, are crystalline in nature. Okay. So I'm going to try to draw a shitty 2D representation of a crystalline structure here. Something akin to this, where let's say that this is a silicon atom. This is another silicon atom. Here's another silicon atom, and I'll keep on filling out this kind of matrix thing here. Okay. So if we're dealing with single crystal silicon, every silicon atom is bonded to 4 of its nearest neighbors. It forms a tetrahedral bond structure. And I'm going to represent those covalent bonds by these double lines, like so. So each of these silicon atoms shares its 4 valence electrons with 4 other silicon atoms so that we wind up with an electrically neutral crystal. Okay. Now, so let me just annotate this. These guys represent covalent bond. This guy represents a silicon nucleus. So let me just put it as a nucleus. So this picture that I've drawn here, or attempted to draw here, would really be kind of representative of what's going on at T is equal to 0 degrees Kelvin or absolute zero, where there's no thermal energy in our system to speak of. So everything is nice and neat and ordered, okay? So at T is equal to 0 Kelvin, our energy band structure would look like this. We've got our band gap, since this is silicon, of 1.12 electron volts, okay? Let me just write this out here. Here's the valence band edge. Here's the conduction band edge. 0 EC plus chi. So as we increase the temperature, we're going to have thermal energy in our system, right? And so these bonds are going to stretch. And eventually we're going to hit a point. Where, so let me just write at T greater than 0K, we're going to have something akin to this, right? So I'm going to draw my silicon atoms again. And this is definitely a simplification, but I think you'll catch what I'm throwing. So these bonds, totally fine and normal. But the bond between these 2 silicon atoms in the middle row has become stretched due to thermal energy, right? So these atoms are going to simply vibrate, and there might be a point where they're vibrating in the opposite directions, that bond becomes stretched, and essentially what's going to happen is that that covalent bond, for lack of a better word, is going to snap like a rubber band, and it's going to emit an electron hole pair. So on the energy band diagram, what that's going to look like is something like this. So for the most part, that guy is still full. So it just goes backwards. And for the most part, our conduction band is still empty, but as the temperature increases, we're going to see that it's possible for an electron to get excited up into the conduction band somewhere. And then over time, it will drift down and fall into the lowest available energy state in the conduction band itself. Okay. So if that electron and that hole ever meet each other, then that electron can drop back down into the valence band, annihilating the electron hole pair in a process called recombination. So essentially, this is a process that's going on constantly when we're at a temperature that's above 0 Kelvin, right? Eventually, there will be enough thermal energy to cause one of these covalent bonds to release an electron from the valence band up into the conduction band. And then over time, as it moves through the crystal, it'll find a hole and it'll recombine. As our temperature increases, the amount of times this happens also tends to increase, and there will be a given amount of surviving electron hole pairs at any given moment that are available for electrical conduction, right? So we'll have some number of holes in the valence band that are free to move about the crystal. We'll have some number of electrons in the conduction band that are free to move about the crystal. And these are what allows for electricity to be carried through our semiconducting medium, okay? So we're going to say that the number of electrons available for conduction is going to be N, okay? So this is going to be the electron concentration typically measured in electrons per cubic centimeter. This will be equal to our hole concentration, P. I regret using red for that annotation, but it'll be fine. So this is our hole concentration. Also measured in per cubic centimeters. And these will be equal to N sub I, which we're going to call our intrinsic carrier concentration. Also measured in per cubic centimeters. Okay? So for every electron that's released, a hole is also released. So there's going to be an equal amount of electrons and holes through this process, at least what we're dealing with right now, okay? So what we're dealing with right now is what's called an intrinsic crystal, meaning that we just have a raw section of silicon. And what I want us to do really quickly, going to do a little bit more background stuff here, but we're going to calculate what's the conductivity of silicon here in just a moment. So before we get into that, we're going to say that this intrinsic electron concentration, N sub I, is going to be B times temperature to the 3/2 power times the exponential of negative the energy band gap, sorry, that's a Q, not a G, divided by twice kBT. So this B right here is some material dependent parameter. At least that's how it's described in a textbook. I'll talk about it more in just a second. So material dependent parameter that has units of kelvins to the negative 3/2 power times per cubic centimeter. And this material dependent parameter is a vast oversimplification of the effective density of states in the valence and conduction band that has to do with the effective mass of electrons and holes in the conduction band and all of that kind of stuff. It's a bunch of quantum physics that is completely and utterly beyond the scope of this class. So we're going to be lazy and just say that's a number that has those units and move on about our day because we don't need to really know that other stuff, right? This T, like I said a moment ago, is simply temperature measured in Kelvin. That's the same T that's over here in the denominator of our exponential function. Eg is the energy band gap that we dealt with a couple of moments ago, so I'm not going to label that guy again. Something that you may be less familiar with is Boltzmann's constant. Boltzmann. Boltzmann's constant. Kb has a value of 1.38065 times 10 to the negative 13 joules per Kelvin, or 8.61733 times 10 to the minus 5 electron volts per Kelvin. Where, for those of you that are not familiar with the unit of an electron volt, 1 electron volt EV is just the charge of an electron multiplied by 1 volt. So that is 1.602 and some change times 10 to the negative 19 joules. Okay. So an electron volt is a measure of energy. This term kBT, we're going to see it a lot. This is commonly referred to as the thermal voltage. And this is going to be approximately 25.9 millivolts at a temperature of 300 Kelvin. So that's the thermal voltage at room temperature, 25.9 millivolts. Excuse me. So let's talk about conductivity really quickly. So electrical conductivity, sigma, my apologies for not being able to write the letter sigma well, is going to be equal to the charge of an electron or the charge of a proton times our whole concentration times our whole mobility plus our electron concentration multiplied by our electron mobility. Actually, should do that mu sub n. So let me just make a note here. These mu things are our carrier mobilities. And they have units of centimeter squared per volt second. So this is our mathematical expression for calculating conductivity based on the number of free electrons and holes as well as their mobilities, which are constants. I'm using constant loosely because they definitely depend on temperature, doping, and a couple of other things, but constants that should be available or at least provided to you, okay? So if we were to calculate I guess a better way to put that would be, I calculated the conductivity of silicon using readily available information, and I got 3.013 times 10 to the minus 6 per ohm per centimeter as a conductivity for silicon. And to contrast that, I also calculated the conductivity of copper and got 5.952 times 10 to the positive 5 per ohm per centimeter, okay? So let's talk about this very briefly. So there is a difference, if my mental math here is correct, of about 2 times 10 to the 11 between these two numbers, right? So that would mean, again, if my mental math here is correct, that copper, intrinsic copper, where nothing has been done to it, is about 200 billion times more conductive than intrinsic silicon, okay? So raw silicon, even raw electrical grade silicon, is actually pretty shitty conductor of electricity, okay? In order to make it a good conductor of electricity, we have to add dopant materials, okay? So these are intentional impurities that we are going to add that will change the electrical properties of the material while really having next to no impact on any of the other properties. So nothing particularly, it's not going to change anything physically or anything like that, okay? So the reason why we can get these electrical changes without having any associated physical changes is because the concentration at which we usually dope our semiconductor materials is in the parts per million to parts per billion range, meaning that there is one impurity for every million silicon atoms, or as low as one impurity for every billion silicon atoms, okay? So in order to dope our semiconductor materials, we typically dope them with elements that will give us properties that we want. So if I go back to this periodic table here, we're starting with silicon right here. So if I add some boron, which is one column to the left, that means that it has one less valence electron. So if it takes the place of one of those silicon atoms, that means that there's going to be essentially a hole that's added that doesn't have an electron associated with it. So this is making this have more positive charge carriers available for conduction. Very similarly, if I add a phosphorus atom to silicon, since this is one column to the right, meaning that it has one more valence electron, this is going to say that, well, I now have one element that has 5 valence electrons when it only has 4 silicon atoms to bond with. So there's an extra electron that's free to kind of float around and do what it needs to do, leaving me with extra charge carriers in the conduction band, okay? So I want to talk about this real briefly in a more formal sense here. Okay. So extrinsic semiconductors have dopant impurities added to change the electrical properties of the material. So acceptor dopants like boron and gallium have only 3 valence electrons. So when they replace a silicon atom in the lattice, they leave behind holes in the valence band that are available for electrical conduction. And now I'm going to draw a kind of picture that's illustrating this, looking at an energy band diagram. Okay. So here's my basic silicon energy band diagram for the umpteenth time with you guys. So it's completely full, or really, really close to full. Here's my conduction band, and it's effectively empty, right? So I'm going to put EC here and EV here. So this is our extrinsic, excuse me, this is what intrinsic silicon would look like, okay? Now, if I add a boron atom or a gallium atom, what's going to happen is I'm accidentally going to create an available energy state that is very close by to the edge of the conduction band, okay? So this energy gap right here is on the order of 0.05 electron volts, okay? So that means that it doesn't take a whole heck of a lot of thermal energy in order to excite an electron from the completely full conduction band up into those empty available energy states that now exist in that gap, right? So at relatively low temperatures, we'll see that these extra energy states essentially trap electrons, leaving behind holes, okay? So, yes,
I thought the valence one was on the bottom.
you are right, sorry. EV and EC, thank you for that. You are absolutely correct. Yeah, so it's leaving behind holes in the valence band, which is what I actually wrote up here. I just drew the picture shittily, so thank you for that correction. So in this particular case, at very low temperatures, what we should see is that if Na, this is the number of, actually, I say it's the number of acceptor atoms, but it's really the concentration of acceptor atoms is much greater than the number of intrinsic electron hole pairs, then we get what's called a p-type crystal. Where the number of holes in this p-type crystal is essentially equal to the number of acceptor atoms and the number of, or the electron concentration in our p-type crystal is going to be approximately equal to the intrinsic carrier concentration squared divided by the number of acceptor atoms. Okay. To contrast this, call the donor dopants like phosphorus and arsenic have 5 valence electrons. So when they replace a silicon atom in the crystal lattice, they leave behind electrons in the conduction band. That are available to conduct electricity. And drawing a quick picture for this guy, and this will be the last thing that I do because we only have 4 minutes left of class anyway. Something akin to this. So essentially now I've got these energy levels right here associated with my dopant atoms, okay? So they start with the electron actually in this energy level, but because we only have about a 0.05 EV gap between the edge of the conduction band and that dopant energy level, it's very easy for an electron to jump from here directly into the conduction band, even at quite low temperatures, right? So we have electrons in the conduction band that do not have an associated hole in the valence band. So this is how we make N-type materials. Okay. So in this case, if ND, the dopant or donor dopant concentration is much greater than the intrinsic carrier concentration, then we create N-type crystals or materials where the number or the electron concentration in the N-type material is approximately equal to ND, and the hole concentration in the N-type material is approximately equal to the intrinsic concentration squared divided by MD. Sorry, my allergies are driving me bananas. All right, so this is a good place to stop for today. So we'll continue our review of electrical concepts in class on Friday. I don't think that one will take the full class time. It looks like I've only got about 3-ish pages of notes here to deal with, and I honestly don't know if I need to talk about all of those things. So we might have a pretty short class on Friday, just as a heads up. All right, thank you guys for your attention, and see you on Friday.